So let's move on to the first example of this section. So I've already derived arc length formula. So I'll just write it one more time. So you'll see a couple different notations for this. So let me just point that out. So sometimes you'll see L is equal to, so this we're gonna have the integral from a to b, square root of 1 plus dy dx squared dx. But you also might see, instead of seeing L, sometimes we use S for arc length. I think it's I actually don't know where that one comes from. I think it's just a historical thing. Or maybe there's some word in others, maybe it was named after another word in a different language where the word started with an S. Again, who knows? So I might screw up because I'm used to writing S. But if I write S, I'm talking about arc length. So let's do our first example. So we want to find the arc length of the semi-cubical parabola. We have y squared is equal to x cubed. Between the points, let's see, so we have 1, 1, and 4, 8. And they give you a figure just so you can, figure, or they give you a plot here so you can kind of get an idea of what's going on. So the idea is, the part of the graph we're interested in is this part that I've just highlighted in red. And you can see that, this graph is always positive between those 2 points. So when I'm talking about this integral, I can write y is equal to x to the 3 halves here. So I just solve, this equation right here for y. Because I need to be able to take the derivative of y. And because I'm only interested in, the graph between these 2 points, I'm not going to worry about the minus sign that comes by taking the square root. Okay, so for this, for this formula, if you look again at the top here, I need to figure out the derivative. So my derivative then is going to be dy dx is equal to 3 halves x to the 1 half. And now I just plug that into my arc length formula. So it's going to be the integral from a to b, and you have to think about what you're integrating here. I'm integrating dx, so I'm only interested in the x values. So my bounds then are going to be between 1 and 4. And then we're going to have, so the square root of 1 plus dy dx squared dx. And when you simplify this, I have the integral from 1 to 4, square root of 1 plus 9/4 x dx. And this is a u substitution problem. And again, you can kind of see when you're, looking at this formula here, if you don't pick a really nice function, this is going to be super hard to integrate. So you have to be, if you're trying to come up with examples yourself, you have to be careful with these. So u is equal to 1 plus 9/4 x, du is equal to 9/4 dx. And so now this becomes the integral. Okay, so yeah, this is going to be really annoying. So let's figure out what u of 1 and u of 4 are to figure out our bounds for the integral. So u of 1 is 1 plus 9/4. That's going to be 13/4. And then u of 4 is 1 plus 9 over 4 times 4. So it's 1 plus 9, so that's 10. So that's not as bad as I thought it was going to be. So I'm just changing the bounds on my integral here. So I'm going to have now the integral from 13/4 to 10 of the square root of u because u is 1 plus 9/4 x. And then dx here is going to be 4/9 du. So I can pull the 4/9 out. Square root of u du. And now I can integrate this. So this is going to be 4/9. Square root of u is u to the 1/2, so I'm going to get u to the 3/2 divided by 3/2, evaluated from 13/4 to 10. Oh boy. So when I plug in 10, I'm going to get 4. So just 4/9 times 2/3 u to the 3/2. Let me simplify a little more before I start plugging in. This factor out front doesn't become anything. This is just 8/27. I'm going to have 10 to the 3/2 minus 13/4 to the 3/2. And I guess this can be simplified a little more in the book. This is where I would leave it though. So I'm going to stop there. I think the book takes it one step further. I'm not really concerned about that. Okay. Again, it's not bad. You have to just set up these integrals yourself. But we're going to talk now. So the question now is, what if instead of given y as a function of x, we're given x as a function of y. We get x is equal to g of y. What do we do then? Well, the formula is going to be pretty similar. We're going to get length is equal to the integral from a to b, square root of 1 plus. Now this is going to be dx dy squared. I'm going to have a dy here because I have x as a function of y. I want to do an integral over y in that case. And so, yeah, so let's see an example of how to do this. So again, it's the same formula as before, just x and y are interchanged, which is why this Leibniz notation is really good. Okay, so let's work on another example. So we want to find the arc length of y squared is equal to x from 0, 0 to 1, 1. Okay, so here I have, x is a function of y. I can write this as x is equal to y squared. And so I'm going to set up this integral, and I'm just going to do it instead of dx here, I'm going to do it dy. So first thing I'm going to calculate is dx dy. So I'm just taking a derivative with x with respect to y. This comes out to 2y. Then I can set up my integral. My integral is going to then be the integral from a to b, square root of 1 plus dx dy squared. So I'm going to get 2y squared here. And because y is my integration variable, I'm going to get a dy there. Because I'm integrating dy, I need to figure out what my bounds are. Well, this thing goes from 0 to 1. So this is going to be the integral from 0 to 1, square root of 1 plus 4y squared dy. And now you have to look at this. This is an integral that involves a square root. So this is going to be a trig substitution problem. So we have 1 plus 4y squared. So, you can factor the 4 out, but I think it's easier to just do y is equal to 1/2 tan theta. And if you don't see why I picked that, again, factor the 4 out of the square root. That way you have y squared plus 1/4. And then you would use a different trig substitution. You would use y is equal to, no, actually you would use the same trig substitution. So it doesn't matter. So then we calculate dy. It's going to be 1/2 secant squared y dy. So I guess we can change the bounds on this if we want. So these get kind of weird. So let's figure out what y of 0 and y of 1 are. So y of 0 is 1/2 tan of 0, which is 0. Y of 1 is 1/2 tangent of 1, and we're going to call this alpha. You can't evaluate that. It's probably going to be irrational, if I had to guess. But anyway, so we're just going to call that alpha, and we're going to write this as the integral from 0 to alpha, because I'm changing my bounds for the trig substitution. Square root of 1 plus 4 y squared, so 1/4 tan squared theta. And then I have dy, so I get a 1/2 secant squared. Sorry, I shouldn't have, that's my bad. It shouldn't be secant squared y dy, it should be secant squared theta d theta. 1/2 secant squared theta d theta. Let me box that. And now I just keep going. So now it's just a matter of calculating this integral. 0 to alpha, I'm going to pull, so I get a square root of 1 plus tan squared theta, secant squared theta, d theta. 1 plus tan squared is secant squared. So I'm going to get the square root of secant squared, so this is just secant. So secant theta, secant squared theta d theta. This is the integral from 0 to alpha of secant cubed theta d theta. So this one, so we did this one previously. So this integral was, this one ends up being, so this one we did before. You do it by parts in section 7 point, let me see, which one was that? I think it was 7.2, yeah. So I did this one in section 7.2. And so when you do this one, you do it by parts. You know, on a quiz or exam setting, I probably wouldn't give you something that difficult to do. So when you do the integration, what you get is, so you're going to get a 1/2 times 1/2 secant theta tan theta plus the natural log of the absolute value of secant theta plus tangent theta. And again, I think I posted my notes for 7.2, maybe I didn't, but I did this, so you can go back and look at example. So this is example 7.2.8. So this is example 8 in section 7.2. So I did this in my notes. So if you need to see how that's done, go back and look at it. But now I'm going to evaluate this from 0 to alpha. When I do that, I'm going to get a 1/4 secant alpha tangent alpha plus the natural log of secant alpha plus tan alpha minus what I get when I plug in 0. So when I plug in 0, tangent of 0 is 0. So the first term is 0 plus the natural log of the absolute value of secant of 0. And then tangent of 0 is 0 again. So this is 1/4 secant alpha tangent alpha. That's good. Plus ln, the absolute value of secant alpha plus tangent alpha. And then plus ln, so secant of 0 is 1 over cosine of 0. Cosine of 0 is 1, ln of 1 is 0. So all that stuff is 0, actually, that I'm subtracting off. And this is my final answer here. You could evaluate this, with a calculator if you want. So the book goes through and does it one more time. I'm not going to do that because, I wouldn't expect you to do that. So again, remember alpha is just shorthand for 1/2 tangent of 1. I'm going to stop here. Again, what you should be noticing is these integrals are really gross. No matter what we do, we're going to get some example where it's a really complicated integral, and that's just, that's part of this problem. Anytime you do this problem, you're going to get a square root of something that you're integrating. So it is, it does give you something really hard to integrate. But we'll pick things that give you things you can actually do in this case. So I'm going to stop the video here.